Hello everybody, welcome to our GCSE chemistry class on the periodic table. Please feel free to say hello in the chat and let me know you're here. Welcome if you're somebody who's not been to one of our classes before. Welcome back if you're somebody that has. It's really nice to have people coming back. Ooh, just knocked the table. It's really nice to have people coming back. I know we had a GCSE chemistry class. Was it GCSE? Last week. Or maybe it was A-level. We had a chemistry class last week anyway, so it was really nice to see people back again. Hello, Khadija. Very nice to see you. Welcome. Welcome to our YouTube classes. So please feel free to say hello in the chat. Please make sure as well that you've downloaded the slides because they're in the description, so you should hopefully be able to download the slides. That means you can keep them for revision, you can keep them for later. They're really, really useful, I think. But yes, please feel free to say hi and welcome to our GCSE chemistry class on the periodic table. Hi, Zara. Hello again. How are you doing? And hello, Peso. How are you doing? Welcome. Oh, okay, lovely. Hi, Zara as well. Very nice. That's fine. That works. That's absolutely fine. Oh, and hello, Pink. I'm going to call you Penguin. So that looks like that's what your name is. But welcome, very nice to have you guys here. We'll get started in a couple of seconds. We're just going to see if anybody else wants to turn up. But yeah, I'm doing well, actually, thank you. Doing very well. Looking forward to a class on the periodic table. I personally think the periodic table is one of the most useful resources in chemistry. If you can learn to use it, and if you can learn to use it properly in GCSE and A-level chemistry, then I think it's kind of one of the most useful resources. So it's there's loads to be learnt about and loads to be done using the periodic table. So looking forward to this class. Hello, Aaron, as well. Hi, welcome. Very nice to have you. Okay, so I think we should get started if everyone is ready. Let's just sort that out. Okay, so this GCSE class is on the periodic table, as I said. Oh, hello as well. Oh, Zara, that's a great question. I'm not sure about that, actually. I don't know. Feel free to send an email to hello@snapprovides.co.uk. They might have more information than me. I haven't been told about GCSE tutoring yet. I know that our A-level is back again, starting this week, starting last week, sorry. But GCSE, I'm not sure yet. I'm not sure there's been a decision made. So feel free to drop them an email and you know, request and all that sort of thing. Okay, so let's get started. So the periodic table, what are we going to be learning about today? Well, before I say that, I'm just going to introduce myself. I think I recognize a couple of you guys that are here. If you don't know me, I am Alyssa. I'm the lead chemistry teacher at SnapProvise. I have a PGC in chemistry education or in science, specializing in chemistry. Chemistry is my thing. And I've been teaching A-level chemistry and all three sciences for the last 6 years. So I do enjoy science. So this lesson, this session, which is probably going to be just under an hour. We're hopefully going to, by the end of it, understand how the periodic table is structured. We're going to understand what the position of an element in the periodic table tells us about its atomic structure. And we're going to understand how the periodic table has developed over time and how clever the scientists were who came up with putting it together. What we're not going to look at is the different reactivity of groups and elements in the periodic table. And forming ions, what ions different elements form. We're also not going to look at properties and reactions of metals versus non-metals or specific groups in the periodic table. Those are covered in various other web classes. Okay, so again, if you're new to this, then I'll just give a brief introduction about what this is. If you're not, apologies, you'll know all this already. But we pop the specification points from the three main exam boards in the front of all of our slides so that you get an idea for what it is that your exam board is expecting from you to do with the topic that we're covering. So if there's anything that you're unsure about, just let me know. We can flick back to the beginning and double check that you're happy with what they want from you. But the specification is one of the best revision tools that you can use as a student, because it literally tells you exactly what is expected of you for an exam. So that was for AQA. This is the content for AQA that we are going to be covering in this session. These are the specification points from OCR that we're going to be covering in this session. We're not going to be looking at ionic and covalent compounds, however, which is in there, and we're not going to be looking at balanced chemical equations either in this session. And then this is the Edexcel specification. So if you're an Edexcel student, this is what we're going to be covering of yours. Again, we're not going to be looking at, oh, next slide. This bit about explaining this division in terms of the atomic structure of the elements. We're not looking in detail at atomic structure today. Hello to Common Study as well, welcome. So super quickly then, what do we already know? Hopefully this is stuff that we know about from Key Stage 3, or at least from our earlier lessons. But what is an element? How do we describe an element? Or, how do I know what the element oxygen is, for example? What is an element? Can you describe it to me? Can you give me a description? Oh, hello, Abin as well. Welcome. Welcome to our class. Lovely to have you. Oh, lovely. Yeah. Fantastic. This is really good, guys. Yeah, lovely. Good. Fantastic. Well done, everybody. That looks brilliant. It's the simplest type of atom. It's made up of only one type of atom. So all our oxygen atoms, for example, and they all have the same number of protons. Really nice, guys. Very nice. So an element is a substance made up of only one type of atom. And how do we know what the type of atom is? Well, it's got the same number of protons. That's what defines an element. Same number of protons. If it has only got one proton, it is a helium atom. If it is an oxygen atom, it has got 6 protons, etc., etc. As long as it has got however many, not 6. If it's oxygen, it's got 8. Sorry. We can look at the number of protons it's got, and that tells us what element it is. Very nice. What's the atomic number? If I asked you for the atomic number of an element, what am I asking you for? What do you need to give me? So are isotopes considered elements? So an isotope is a slightly different description. An isotope describes something else. There is an overlap between isotopes and elements, yes. An element is it's the type of atom that it is. So elements can be isotopes, or there can be isotopes of an element. I don't know if that makes sense. So yes, isotopes are elements because you can have isotopes of an element. It's kind of like a subcategory of elements, basically. Yeah, lovely, guys. Well done. It looks like loads of people have got it right. So just be careful. Specifically, especially if we're asked for this in an exam, the atomic number is the number of protons. Okay, it's the number of protons in an atom. You're right, those of you that said electrons, it can also tell us the number of electrons, but by definition, it's the number of protons. So you just got to be really careful. If you're asked that in an exam, you need to say number of protons, not number of electrons. And why are atoms neutral? Why do they have no overall charge? And this links back to what we've just been saying. Why do they have no overall charge? What do we reckon? Why are atoms neutral? Why do they have no overall charge? Yeah, lovely. Really good. The number of electrons and number of protons are equal to each other. Good. Yeah, well done. Fantastic. So protons are positively charged, electrons are negatively charged. If you've got an equal number of both, then the overall atom will be neutral. This is when number of protons. Oh, hello. As always, guys, if you can't read my handwriting or if I talk too quickly, just let me know and I will slow down or read something out again. I do try and talk quickly because we've obviously always got a lot to get through and I always want to try and answer as many questions as possible. So please do let me know if I don't make sense or if you can't read my handwriting. Yeah, so the number of protons are positively charged things are equal to the number of negatively charged things. It's not that there isn't a positively charged or negatively charged thing in the atom. They are there. It's just they are equal in an atom. When we go on to talk about ions in another web class, that's what happens when you start taking away some of the positive or negatively charged particles. If you start doing that, or you start adding positively or negatively charged particles, then you're going to start getting charged particles. Okay, lovely, fantastic. So what can you tell me about this sodium atom that I have got represented here? What can you tell me about it? It's got quite a lot of information here that we've been given. What can we take from it? What can we get about from this diagram? Are there any facts that you can tell me about the structure of an atom or the electron configuration or what this sodium atom is made of that we can get from here? And then also, whilst we're doing that, can you give me a definition of an isotope? What is an isotope? Okay, lovely. Okay, we've got some different answers. So just got to be careful. Lovely. Oh, we've got some great answers going on here. Okay, so we're just going to be careful. I think we've had a couple of corrections, which is great, but it's 1 electron in the outer shell. So I think somebody said it's in group 1. Well done, that's lovely. We'll come back to that in a bit. There's 1 electron in the outer shell. There's a total of 18 electrons here. 18, I can't even count. 11 electrons, sorry, not 18. 11 electrons. I just read someone's answer, I think. In total, we have 1, 2, 3 electron shells. And I think somebody gave us an electronic configuration. So we just need to check our electronic configuration is 2, because there's 2 electrons in the first shell, comma, 8, because then there's 8 electrons in the second shell, and then 1, 2, 8, 1 is the electron configuration. You don't need to know that. That's just because somebody put it in, just wanted to make sure that they got that correct. So there's 2 electrons in the first shell. Well, you don't need to know that yet anyway. 2, 8, 1. Okay, and then an isotope. What is an isotope? Lovely, really good. Fantastic. So anybody else agree or disagree with those definitions of isotopes? What is an isotope? They're atoms of the same element, exactly right. So atoms of the same element. Now we can say the same element because that's saying, because that's true, but it's in an exam, it's better to also say that they have the same atomic number and or they have the same number of protons. Now, I know they're kind of saying the same thing, but if you mention one of the other 2 things, you're showing your examiner you know what that means. So the same element with the same number of protons, or the same atomic number, you can say, but a different number of neutrons, or again, you can say, but with a different mass number. That's also fine. Same atomic number, different mass number, or same number of protons, different number of electrons. Both are fine, but a different number of neutrons. So same number of protons is basically means they've got the same atomic number. And different number of neutrons mean they've got a different mass number. Okay, how are we doing? As usual, guys, please feel free to pop in the chat any questions. I do try and keep on top of the chat. If I miss your question, it's because too many things have gone past and I haven't seen it. So just pop it again if I don't answer it, or if somebody else wants to answer it, please feel free to. And if you're not sure, we can have a chat about it. Okay, so the structure of the periodic table. Let's go through this super quick, see how much we can remember about the periodic table, or how much we already know, and then we can fill in any gaps. So what is it that's displayed in the periodic table? It's the periodic table of what? And then how do we order our elements? What is the main order in the periodic table? So there's two things for you. It's the periodic table of elements. Good. So that is what we're showing. We're showing the elements, the different types of atoms that you can find in our universe. And then they're ordered by, yeah, good, well done. They're ordered by atomic number, good, or by number of protons. And I'm just going to go one step further and just say increasing atomic number. So we go from 1 with hydrogen all the way up to 118 right at the bottom, which is, I've forgotten what that one's called. I used to know it. Tennessee, is it? Is that 118? I can't remember. But yeah, so it's ordered. Our main way of ordering it is by increasing atomic number. Now, when you get questions like this in an exam, it can be really hard to work out what they're asking. Are they asking you to talk about its order, or are they asking you to tell you how they're grouped? So you've just got to be really careful when reading these kind of questions. Okay, so we've looked at sodium. So this is our element, our chemical symbol. Which of these numbers is the mass number? Is it 23 or is it 11? Is it 23 or is it 11? Which is the mass number? And then we've also got our name here as well. Good, it is 23. The more massive of the two numbers is the mass number. The bigger or the more massive of the two numbers is the mass number. And the bottom one, the smaller number, in this case, the bottom one, it's not always on the bottom, but the smaller number is the atomic number. So just to double check, and that's the proton number. Good. Mass number, which is protons plus neutrons, and atomic number, which is just protons. Fabulous. Okay, let's keep going then. Unless anyone has any questions, let's keep going. So why is it called a periodic table? What's it periodic? Does anybody know what this term period means? If you're talking about a period, it's kind of a bit of a loose term, the term period, but it usually, when we talk about it in terms of like repeating things. The period of something is yeah, you're right, a period is an amount of time, but it's a repeating pattern. Yeah, good, okay. So this is called the periodic table because periodically we get repeating patterns of reactivity, of structure, etc. So table is called a periodic table because similar properties occur at regular intervals, at periodic intervals. Regular or periodic intervals, which I can't spell. Intervals. Okay, so yeah, it's a period of something, repetition of something. Can we say due to the arrangement? I'm not sure what you're asking there. I'm afraid. I'm not sure. Might need to ask a question again there. I'm not sure you say what you mean. Okay, so name me some groups in the periodic table. Hopefully we know that it goes 1, 2, 3, 4, 5, 6, 7, 8, or 0. What's the name of any of these groups? Do we know? What's the name? And the other thing that we need to know is where do we find the different types of elements, different types of atoms? There are two main types of atoms, metals and non-metals. Where do we find them? If you're going to name a group, do you want to tell me which number group it is? Just so we can check that we're happy. covering the arrangement of the periodic table. Oh, I see what you mean. Yeah. So there's a repeated pattern that covers the arrangement of the periodic table. Yeah, I think that works. Good. So we've got halogens, we've got noble gases. So our halogens in here are green, group 7 halogens. We also need to be aware of our blue group, which is our noble gases. Noble gases. Lovely. We have our alkali metals in red. We need to know what they're called. Alkali metals. We also need to be able to name that one. There are earth metals, but we don't actually have to name those at GCSE, which is quite good. And then we've got metals and non-metals, which I think people have said as well. That's the split down the staircase. So our staircase goes like that. And our metals are on the left. And if you're ever not sure, if you can ever not remember, find something you know. Here we've got silver and gold, copper, silver and gold. Often we know that copper, silver and gold are metals. So find which side of the copper, silver and gold are, they must be the metals. And then our non-metals are on the right. And yeah, lovely, those of you that said our middle section are transition metals, but that's covered in a different class, so we won't do that in too much detail now. Okay, so halogens is just the name of the group. Group 7 is a bit like it's just naming a group of them. This group, fluorine, chlorine, bromine, iodine, and acetine, are all halogen elements. I'm not sure whether the name comes from the light bulb or the light bulb comes from the name. I think the light bulb comes from the name. So somebody decided that they were going to be called the halogens, and so they were called the halogens. Alkali metals, there is a web class on group 1, but they're called alkali metals because the fact that they form alkaline substances. This group form alkaline substances when it reacts with water. That's why they're called alkali metals. And then noble gases is group 0, sometimes known as group 8, but I'm going to call it group 0, is our noble gases. It's called noble gases because they are considered very unreactive, very inert. Very nice. Okay, let's keep going. How are we doing for time? Not too bad. Let's keep going though. Okay, so it looks like lots of us are comfortable with this, but let's just double check. What are the groups in the periodic table and what do they tell us? What information do they give us? And then what are the periods in the periodic table? What are we looking for when we look for periods, and what do they tell us about our elements? So what are groups and what are periods? And then if you know what groups and periods are, can you tell me how many outer electrons our alkali metals and our noble gases have? How many outer electrons do our alkali metals and our noble gases have? So what's a group? What is a period? And how many electrons do our group 1 and group 0 elements have? Really nice. Fantastic. Okay, double check, total recall, just double check yours because I'm not convinced that one of your answers is right. So just check that one. Cool, okay, it looks like we've got pretty good understanding. So let's just double check. The groups are the columns, they're the vertical columns. They are the oops, that doesn't look like a V, does it? Oh no, there we go. Vertical columns, and they tell us the number of outer electrons, or the number of electrons in the outer shell. Oh, oops, that didn't work, did it? The vertical columns, they tell us the number of electrons in the outer shell, or outer energy level, but I'm going to call it a shell. And then our periods, if we remember, the number of periods it is. Periods of the rows, the horizontal rows. And they tell us the number of shells. The number of electron shells in an atom of an element. Nice, good, lovely. So well done, fantastic. We spotted it there. So alkali metals have one outer electron. They're in group 1. In group 1. And our noble gases, which are technically in group 0, but we can call it group 8. Mostly we should call it group 0. They have, oops, I need to put 0 there. They have 8 outer shell electrons. Apart from one element, one noble gas hasn't got 8 electrons. Which noble gas hasn't got 8 electrons? Which one hasn't got 8? Are noble gases considered inert elements? So they're not considered inert, they are inert because they've got a complete outer shell, yeah. So elements react in order to get as full an outer shell as they can. That's why they react. That's the whole point of it, because it makes them more stable. And so, yeah, noble gases have already got a full outer shell, so they don't need to react. There's nothing causing them to react. So, yeah, exactly. Very nice. Yes, well done. Helium, number 2. It's only got 2 electrons, so it can't have an outer shell of 8 because it's only got 2 electrons. Helium has 2. So it's still a noble gas because technically it's got a full outer shell because the first shell can only contain 2 electrons. So it's got a full outer shell. So it's still a noble gas. Oh, come on. It just doesn't have 8. So just double check that you're happy. And so the group is the vertical columns. The vertical columns are the groups. Okay. Very nice. Let's keep going then. So our electron configuration then, we're going to have a look at fluorine. Now it takes a bit of practice, does take a bit of practice, but it's really useful, or can be really useful, to use the periodic table to decipher the electron configurations of an element. So if we've got fluorine, for example, I can very quickly decipher what its electron configuration is without having to count out electrons, because fluorine is in group 7 and period 1, 2. It's in period 2, group 7. So if it's in period 2, it's got 2 electron shells, so I can draw those in. 1, oops, let's do that a bit better. 1, 2. So I've got 2 electron shells, and its outer shell has got 7 electrons in it because it's in group 7. So I can put my 1, 2, 3, 4, 5, 6, 7 electrons in the outer shell. I know that if it's got to period 2, if it's got to shell number 2, all the previous electron shells must be filled. So I know that my shell 1 has got to be filled. And shell 1 can only take 2 electrons when it's full. So I have to put my 2 in there. We haven't saved ourselves a huge amount of time with fluorine, but if we were trying to do iodine, no, that's a bad example. Chlorine, for example, rather than having to draw out 2 electrons and then 8 electrons and then another 7 electrons, which can take a little bit longer, and you'd have to count them all out every time as well. It's a lot quicker if you then just work out what period we're in. So in chlorine's case, it would be period 3. That means there's 3 shells. What group's it in? 7. So it's got 7 in its outer shell, and every earlier shell, every smaller shell has to be filled. So then we just whack them all in. Did that not make sense, Total Recall? That didn't make sense. We'll have another go in a second. We'll have another go with another one. So just to recap, fluorine has got 7 outer shell electrons. So it's got 7 in its outer shell, and it's got 2 shells. So the first shell must be full. Otherwise, we wouldn't have moved into the second shell. If the first shell is full, so it must have 2 in it. And then the outer shell's got 7. Yes, that's A level, that configuration, but yes, it would be. I know, exactly, but that's because often we don't get taught about it in that way, because there's loads of other things you have to know about electrical configuration. So, but it can be that easy. Can be that easy. In which group does metal like scandium, titanium, etc.? So, Albin, this is where we get, if you're going on to A level, it starts getting a little bit more complicated, because although even at A level we consider group 1, group 2, group 3, group 4, you can then start considering these middle ones as being groups as well. And you actually then end up going up to group 18 rather than group 8. So at GCSE level, we just consider all of these to be transition metals. That's what we give, that's the name we give them, because they are transition metals, and we don't define it any further than that. So at this level, you don't need to know whether it's got a group or anything like that. You don't have to know anything about the electron configuration of any transition metals. You will only be asked to do the electron configuration of up to calcium. So up to element number 20 here. Okay, so you don't have to worry about the electron configuration of any of the transition metals, not at GCSE anyway. Okay, fantastic. Let's keep going then. Let's try another element. So use the periodic table below to determine the atomic number of magnesium. So again, if we're determining the atomic number of magnesium, previously we've discussed that the atomic number is the number of what? Atomic number is the number of protons. If the atomic number is the number of protons, but this is an atom, we're talking about an atom because it's not mentioned in an ion or anything, so we're talking about an atom, then we know that the number of protons, or in an atom, the number of protons is equal to the number of electrons. So let's work out how many electrons it's got. I mean, if you're just going to look it up on the periodic table, that's cheating. We need to use unlike your period, we need to use the periodic table. Well done if you've worked it out using the electron configuration though. Let's work it out. So how many electrons are in the outer shell and how many shells has it got? How many electrons are in the outer shell? How many shells? How many outer shell electrons and how many shells, electron shells for magnesium? How many outer shell electrons have we got in magnesium? It's here, if you haven't found it, magnesium. How many outer shell electrons has it got and how many shells? Looks good, guys. Yeah, okay, fabulous. So it's in group 2. All of these elements are in group 2, so all of these elements have 2 electrons in their outer shell. It's got 2 outer shell electrons, and it's in period, we often forget, don't forget about hydrogen and helium are in period 1. Don't forget about them, we often do. So that's period 1 at the top, don't forget about it. Then period 2, then period 3. So it's in period 3 and group 2. So it must have 3 shells, 2 outer shell electrons. The first shell must have 2 electrons in it because it's full. The second shell must have 8 electrons in it because it's full. And the third shell, third shell is the outer shell, and it's got 2 shells, 2 electrons in it because it's in group 2. Oh, I can't do my equals sign for some reason. So total then, 2 plus 8 is 10 plus 2 is 12. So really good, well done those people that said 12. That's fantastic. Okay, double check that you're happy that it's got 3 shells. Yeah, it's in period 3, group 2. So it's got 3 shells, and in the third shell, in the outer shell, is 2 electrons. Anybody not happy with that? Yes, you can, but we don't tend to use the term valence again until we get into A levels. But yes, you can call them valence. What's a group again? Who can tell me what a group is? Well done, total recall, fantastic, straight in there. It's the vertical column are the groups. Groups are the vertical columns. period is the row. A group is the column, and the period is a row. Okay, Harleen, so how do we know it's 12? So what I've done is I've taken its position in the periodic table and used that to work out that it's got 12 electrons. If it's got 12 electrons, it must have 12 protons. We can draw a picture of it. We've got, if I just prove it with the electron configuration on the next page. So let's draw a picture. So we said we've got 3 shells because it's in period 3. So it's 3 electron shells. 1, 2, 1, 2, 3. Its outer shell is in group 2. So its outer shell has got 2 electrons. That's what the group tells us. So I know it's got 2 electrons in its outer shell. They're not going to be paired because it doesn't like pairing if it can help it. And in order to finish this diagram, I have to fill all of the inner shells. We don't put any electrons into the outer shells until we've filled all of the inner ones. We have to fill from the inside out. So shell 1 and shell 2 must be full. Shell 1, we said, can carry 2, a maximum of 2 electrons. So it is. Shell 2 can carry a maximum of 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. So total number of electrons for magnesium is 2 plus 8, which is 10, plus another 2, which gives us 12 electrons. So if there's 12 electrons, there are 12 protons. Fantastic. Okay, right, let's keep going then, guys. How's everybody feeling about all of that? How confident are we feeling? How are we feeling? If you give me a number, so, or a smiley face, so 1 and a smiley face if you're feeling good, 2 or a medium face if you're feeling all right, yeah, this is okay, and 3 or super confused if you are not feeling so good at the moment. Harleen, do you count from hydrogen to magnesium to find? You can do, but what I'm saying is there is an easier way that links together all of our knowledge and reminds us of all of our knowledge about groups and periods and stuff. The easy way is to count along. You can do that, but A, with some of the longer, bigger elements, it takes forever. And B, we need to start thinking about what groups and columns represent, and it helps us to link all of that knowledge together. Okay, brilliant. Fantastic, well done, guys. Lovely. Glad everyone is, well, most people are doing okay. Let's test ourselves. So can you tell me which element W, Y, and Z are? Pop in the chat. So W is what, Y is what, and Z is what. Can you tell me, we've got a periodic table here. We've been given the electron configurations. So using our knowledge about what the electron configuration is telling us, about what we know about groups and periods, can you tell me what your elements are? What do we think? Anybody got any ideas? Oh, we've got some people having a go. This is fabulous. Well done. Oh, it looked okay. So it looks like we've got W sorted. Well done, guys. So W, it's in 1, 2, period 3, because it's got 3 electron shells. It's got to be in period 3. So that's 1, 2, 3. And it's got 1 electron in the outer shell. So that one must be sodium. Really well done if you got that. Fantastic. Y, what about Y? So again, we've got 1, 2, 3 electron shells. So it's got to be in period 3, but the outer shell has got 8 electrons in it, so it's got to be in group 0, otherwise known as group 8, but group 0. So that one must be argon, so really good if you said that as well. And then finally, element Z has actually got 1, 2, 3, 4 shells, so it must be in period 4, but it's got 1 electron in its outer shell, so that one must be potassium. So really good if you got that one. Fantastic if you've got all 3 as well. Really nice, well done. Fabulous. Okie dokie. Really good. Let's keep going then. So that's 3 marks, 1 for each of them. 1, 2, 3. Perfect. Sodium and potassium, this is the next part of that same question. Sodium and potassium are members of the alkali metals. Explain in terms of their electronic structures why both elements are placed in group 1 of the periodic table. What do we know about sodium and potassium in terms of their electronic structures, which tells us why they need to be in group 1? What do we think? It's only worth 1 mark, so we only need to say one thing. It's an explain, so we just need to kind of, we need to explain why, what's the reason why they're in group 1. Really nice. Yeah, lovely, fantastic, guys. So they're in group 1 because they have 1 electron in their outer shell. Or we can say their outer shells contain 1 electron, or they have 1 outer shell electron. They have 1 electron in their outer shell. Anything along those lines is correct. Really nice, well done. Fantastic. Right, I'm going to need to speed up a bit because I am being slow. Okay, let's have a look. Let's keep going. So the next bit we need to know is people often find it a little bit less interesting, but it's incredibly important as scientists for us to be able to describe or to understand how scientific ideas develop. Because when we first come up with scientific ideas, people either go, well, that's a load of rubbish, or they go, yeah, okay, I'll follow that, that's fine. And as time goes on, as people investigate things more, you can prove or disprove things. And that's one of the wonderful things I think about science, is that we can keep finding out new things. We can keep refining our ideas. We can keep having new ideas. And it's, I think it's amazing. So let's talk about the development of the periodic table. Where did it come from? So initially, we only knew a handful of elements. These were things that we could find, for example, lots of the gases. We knew about carbon. We knew about some metals. And so scientists didn't know what these elements were. They thought that they were tiny balls of atom, and they were just different types of atom. So the only way they could measure them was by their weight. So the elements were arranged, therefore, in order of atomic weight. Notice this is different to atomic mass. This is literally their weight. How much did they weigh when we had different amounts of them? So the heaviest things, like iron, went to the bottom of the periodic table, and the lightest things, like hydrogen, went at the top. So this was ordered by their atomic weights. What was the issue with this, though? What's the issue with this as a periodic table? What's wrong with it? What's wrong with this as a periodic table? Anybody know? What's missing? Why can't we use this as a periodic table? It's a good guess, actually, but not quite. Yeah, so we're missing a lot of detail, definitely. We're missing a lot of detail. The main thing is, how many elements have we got here? 3, 6, 9, 12, 15. We've only got about 20 elements, 21 elements. So we're missing a load of elements. Yeah, good. So the table was very incomplete. We were missing a lot of elements. And as I think some people have said as well, they're not arranged in appropriate groups. They're not with their similar elements. Okay, no worries. We're just about to look at a different one, so that's fine. So they are arranged in groups with repeating patterns. So they knew, for example, that hydrogen, fluorine, and chlorine reacted similarly to different things. So they had similar reactivity or patterns of various kinds. So it could be to do with their weight, it could be to do with their density, it could be to do with their reactivity. So they were grouped with elements of similar reactivity, but some elements are in the wrong group or inappropriate groups. Inappropriate groups. So for example, oxygen is a very different element to iron. Now, they have some things that are the same, but they are actually fundamentally very different elements. So they tried to group them together. They tried to put them in groups that were appropriate, but they had to kind of force some into groups a little bit to try and make do. Okay, so then we found a few more elements, and we had a little bit more of a chance to kind of focus them a little bit. So we came up with a little bit more structure to our periodic table. So it's not just kind of 7 groups in groups of 3. We didn't have our triads. That's what the previous one, we can describe it as triads, groups of 3. We had a little bit more detail. We could do a little bit more sophisticated ordering. Does anybody know the name of the scientist? I think I've seen his name in the chat, but what's the name of the scientist that came up with this development, kind of what we would consider to be our main development before the modern periodic table? Yes, really nice. We'll come to that in a second. It is Mendeleev. Yeah, good. Mendeleev. Now, he was particularly clever, and we need to pay a particular attention to how he arranged his. And I think I've seen people as well. What did he do? Well, and it was very, very like poo-pooed by a scientific society. He left gaps. Why did he leave gaps? Why did he leave gaps? And why did society say, what on earth are you doing? You're a nutter. Why did people not like it? Brilliant, well done. He left them for undiscovered elements, ones that were going to be discovered in the future. So by doing that, he basically said to the rest of scientific society, I don't think you're good enough. I don't think we're good enough because we haven't discovered all the elements. I think there's still more for us to discover. And a lot of other scientists went, how dare you? We're the brightest minds here. We think we found everything. How dare you tell us that we're wrong? And he was the first big name to say, actually, I think we're wrong. I think there are missing elements that we will find at some point, but we haven't yet. So for a long time, people said, he doesn't know what he's talking about. But he did know what he was talking about. He also, if we have a look here, we've got an increasing atomic weight again. So we're increasing in our atomic weight as previously. But what happens here? It's increasing, increasing, increasing. And then suddenly, tellurium and iodine swap places. What's he done there? Why has he swapped the places of tellurium and iodine? It was all increasing mass, increasing mass, increasing mass, increasing mass. And suddenly he went, actually, no, I don't want to put those two in increasing mass. I'm going to put them the other way around. Why? What did he decide about his groups? So it's a good point, actually. Is it to do with their subatomic particles? It's not. We weren't that clear yet about what subatomic particles were present in atoms when Mendeleev was doing his table. We hadn't worked it out yet. So it's not actually about subatomic particles. It turns out to be, but Mendeleev didn't know that at the time. So it's to do with the fact that iodine reacts very similarly, I mean, not with manganese, because he was a little bit not so good with the transition metals. He's kind of stuck them in the middle a bit. But fluorine, chlorine, bromine, and iodine all react very similarly. And so Mendeleev said, hold on, I don't like the fact that iodine should, in terms of increasing atomic mass, should be one step over. I don't like it there. I'm going to put it in the wrong order according to atomic mass so that it fits with chlorine, bromine, and iodine, because they react very similar. So he swapped the places of some elements to fit with the reactivity. And again, this was poo-pooed by some scientists as well, who said, well, you're just going against your own rules then, what are you doing? But he knew that iodine fit much better with chlorine and bromine and fluorine than it did with oxygen, sulfur, selenium, and tellurium, etc. And he knew that tellurium fit much better in that group as well. It turns out it's because of the number of electrons it's got, but he didn't know that at the time. He just knew about the reactivity. So he's really, really clever, really, really clever. I just realized I've talked too much and we're not going to be able to do the exam questions on this. Never mind. Let's just finish up the modern periodic table then. Oh yes, so we can, if you go to CERN, which is an incredibly exciting trip, if you manage to go to CERN in Geneva in Switzerland, you can have a look at all the different, they're trying to find as many different types of elements as they can. Now, I think the majority of people assume that we have found all of the elements from 1 to 118, but there are different iterations, different types of these elements, so different isotopes basically, that we maybe haven't discovered of our elements from 1 to 118. I think people are still trying to make basically the next row on the periodic table, but whether they're going to be able to, we don't know. A lot of the last row that we haven't got on this periodic table, but a lot of the last row don't exist apart from in a lab. So whether or not we can really call them atoms and elements is up to discussion, but I think they're looking to see if they can, but whether or not they can exist, we don't know. Okay, so right, let's just speed through this last little bit then. So in the modern periodic table, what do we have to state that they are in order of what? What are they in order of? Increasing what? Now that we know more about their subatomic particles and stuff, we are arranging them, in increasing what? How do we arrange them? It is increasing atomic number. That is how we arrange them in order. So they are in order of 1, 2, 3, 4, 5, 6, number of protons, a number of atomic number, or their atomic number. And we don't arrange them in order of atomic weight because that would mess things up a little bit. So we just look at order of increasing atomic number, AKA proton number, exactly, number of protons, fantastic. And then we know that there are over 100 elements, currently 118, but as you say, we are, or as we've said, they are looking to see if they any more exist. Personally, I don't think we can say that anything more than 118 exists because, like I say, when you get up to 118, they exist for microseconds in the laboratory before the atom breaks apart into smaller atoms. Because the bigger they get, the harder it is to kind of keep them together. So, because you're trying to push a load of protons that are all repelling each other into a tiny, tiny space. And the more you've got, the more they're going to repel each other. So the bigger and bigger atom you get, the harder it is for them to stay together. And therefore they don't exist for very long before they fall apart again. So whether or not we can call them atoms is up for discussion, but they have decided that there are 118 that they can make in a lab, or they can prove exist. There are 118 at the moment, because we found all the missing ones. Okay, I think that was everything that we needed to know. They're in order of increasing atomic number, but they're also grouped by reactivity. We also need to say that as well. They are grouped by reactivity. That means every element in group 1 reacts similarly, not the same, but similarly with different elements. Every element in group 2 reacts similarly. Every element in group 7 reacts similarly. Every element in group 0 reacts similarly. So they're inert, etc. Cool. Okay, so how's everyone feeling about that? How are we all feeling about that? Anybody still super confused, or are we all feeling fairly confident about that? Or yeah, it was all right, might need to revise a little bit again. That's absolutely fine. You can just let me know that's all fine. Fantastic. Lovely, really good. Thank you very much. Well done, guys. Lovely. Okay, I'm really sorry, but because I've talked too much, we're not going to be able to have a go at those questions. But every bit of information that you should need to answer those questions should be in the previous slides that we have just covered. So please feel free to have a go at answering those questions and just check that you're okay with recalling that info. But hopefully now we should be able to understand how the periodic table is structured understand what the position of an element in the periodic table tells us about its atomic structure, and understand how the periodic table has developed over time. Okay. Just before we disappear, just want to let you know about our upcoming web classes. So if you're interested in some GCSE maths, physics, or biology, these are our upcoming web classes. This is our schedule. Please feel free to have a look. We've just popped the schedule in the chat as well, so you can have a look there. Feel free to set a reminder on YouTube so you can come back and have a look at our lessons, because obviously they're free for you guys and they stay on our YouTube channel, so you can rewatch them. You can rewatch them for your revision, etc. So please feel free to do it at your leisure as well. If anybody has any questions, feel free to ask now. Otherwise, I'm going to disappear because I've got an A-level class in 5 minutes' time, which I need to set up for. So if you have any super quick questions, please feel free to drop it in. Otherwise, you can send a message to hello@snapprovise.co.uk, and we will try and get back to you and respond to your questions there. If you fancy coming along to the A-level class as well, please feel free to do so. We're going to flip over onto that channel in a minute. So the A-level class should be up on our website, on our YouTube profile as well. So you should be able to find it on the A-level class. It's on mass and moles. So I will see you there. Okay. If anybody has any questions, please send it to hello@snapprovise.co.uk, and I will see you guys very shortly. There will be another chemistry GCSE class. It's just not in the next month. It's just over a month. So I'll hopefully see you guys then. Thank you very much, guys. If you're coming to A-level, I'll see you in A-level. Bye. Thank you very much. Thanks, guys. I will see you soon.